talked about intrinsic semiconductors, which are pure semiconductors. They don't have a lot of a large number of carrier concentration, electrons or holes, which may be thermally generated in a lattice of a pure semiconductor crystal. So what we can do is to improve the generation of improve the conductivity of the material and generate an electric current. We can add an impurity to semiconductor materials, and these semiconductor materials are known as extrinsic semiconductor materials. So since the electron and hole concentrations in a pure semiconductor or intrinsic semiconductor are relatively small, only very small currents are possible. Okay, so what we intend is to increase the concentration of holes and electrons by adding or introducing some impurity atoms from group 3 and group 5 elements into the silicon lattice. So these concentrations, can be greatly increased by adding certain impurity. For example, if you are going to introduce group 5 elements like arsenic or antimony or phosphorus, you see that they have different valence structure. I mean, they have 5 valence electrons, and 4 of which can be contributed into the covalent bonds, and one is can easily break free into the lattice at ordinary room temperatures and can contribute to the conduction of current, for example. Okay, so that way we can increase the number of charge carriers and hence the electric current. So a desirable impurity is one that enters the crystal lattice and substitutes one of the semiconductor atoms, even though the impurity atom does not have the same valence electron structure. It could be different. For example, I mean, instead of group 3, you can also have, instead of group 5, you can also have group 3. For example, you can have a boron doped silicon lattice or germanium lattice, right? Now, boron has 3 valence electrons, and 3 of them can be used to create covalent bonds with neighboring 3 silicon atoms, and one of them, which is vacant, nearby or adjacent electron is going to come and complete the octet structure while leaving a certain hole at that place. So they can reduce holes. For example, group 3 impurities you will see will introduce holes, and group 5 impurity will introduce a majority of charge carriers that are electrons. Okay, so this is going to be the situation. So we can have impurities from either group 3 elements or group 5 elements. Okay. Now for silicon, the desirable substitution impurities are from group 3 and group 5 elements. So let's have a look one by one. Now this figure 1.6 shows a phosphorus atom, you see, which has a different valence structure. Now this is going to form the bond over here with 4 neighboring silicons. Okay, so it's going to complete its octet structure nonetheless. 4 electrons are shared, and you see this impurity can be, let's say, 1 by 10 to raise power 6. Let's say 1 out of 10 to the power 6 silicon atoms. It's a very small ratio by which the doping can be done. But you see, for each given phosphorus atom introduced into the lattice, we have 1 free electron which is very loosely bonded in the covalent structure, and it easily gets energy to elevate itself from the valence band to the conduction band and then start contributing into the conduction. So this is one way you can increase the charge concentration in extrinsic semiconductors. So this part A shows the 2-dimensional representation of a silicon lattice, which is doped with a phosphorus atom from group 5, showing the 5th phosphorus valence electron, okay, which is free, which is loosely bonded. Now you see, this phosphorus atom has a positive charge, net positive charge, because it is the deficiency of electrons. And although still the lattice is electrically neutral, but it has free charge carriers which can, increase the concentration of free charge carriers in the conduction band, and they can contribute to the conduction. So in figure B, you have the resulting positively charged phosphorus ion after the 5th valence electron has moved into the conduction band. But this doesn't mean that phosphorus is going to be conducting. This atom does not conduct. Okay, this ion is not contributing to the conduction of electric current. However, this electron in the conduction band is now going to conduct. Okay, keeping the lattice electrically neutral. So the most common group 5 elements used for this purpose are phosphorus and arsenic. For example, when a phosphorus atom substitutes for a silicon atom, as shown in 1.6a, 4 of its valence electrons are used to satisfy the covalent or octet structure. Now the fifth valence electron is more loosely bonded to the phosphorus atom, and at room temperature, this electron has enough thermal energy to break free from the valence band, and it breaks the bond and is free to move through the crystal and contribute to the conduction of electric current in the semiconductor. So when the fifth phosphorus valence electron moves into the conduction band, a positively charged phosphorus ion is created. Okay, but mind you that this phosphorus positively charged ion is not contributing in any conduction of electric current. It's the charge carriers which are responsible. Okay. Now this type of impurity is the donor impurity. Why it's the donor impurity? You see these group 5 elements, they have a different valence structure. They have one extra electron which can be contributed into the conduction band. Therefore they are donating the charge carriers. So these are known as donor impurity. Since it donates an electron, so it's free to move. Although the remaining phosphorus atom has a net positive charge, the atom is immobile in the crystal and cannot contribute to the conduction of current. So therefore, when a donor impurity is added to a semiconductor, free electrons are created without generating holes. You see there is no generation of hole. The electron is coming from the impurity atom. In this case, it's a group 5 phosphorus atom. So this process is called doping. It allows us to control the concentration of free electrons in a semiconductor. The semiconductor that contains donor impurity is called N-type semiconductor for the negatively charged electrons, and it has a predominance of electrons compared to the hole. And such extrinsic semiconductors, which has group 5 donor impurities, they are known as N-type semiconductors. Why they are N-type semiconductors? Because they have a majority of free charge carriers that are electrons, that are primarily that have a predominance of electrons as compared to holes. Okay, we're not creating holes. It's not like electrons which are breaking the bonds as an intrinsic semiconductor and leaving holes behind. It's the loosely bonded electrons which get enough energy to conduct, to get themselves elevated into the conduction band and start conducting through the lattice. These are N-type semiconductors, okay, which means the majority carriers are electrons. And then similarly, you will see that for group 3, acceptor impurities like boron, which is going to accept electron, and let's say if there is a boron atom which replaces a silicon atom, it's going to be negatively charged. Okay, therefore it's going to create holes, and the conduction of current will be due to the hole. So these semiconductors, on the other hand, are known as P-type semiconductors because the majority carriers will be holes, and the current conduction mechanism is based on the hole current. It's not the electron current. Okay, so now again, most common group 3 element used for silicon doping is boron, let's say, and when a boron atom replaces a silicon atom, it has 3 valence electrons, which is used to satisfy the covalent bonds requirement for the 3 of the 4 nearest silicon atoms. For example, over here, you see boron has 3 valence electrons, and it can form a covalent bond with the 3 of the 4 neighbors of silicon atoms. So out of 4, there are 3 silicon atoms which are bonded in complete duplet structures. But here we have one less electron, so it's positive, right? So what happens is that from an adjacent bond, let's say over here, the electron, it might break free due to the thermal energy, and it might fill in for the octet structure, giving boron an overall negative charge. Now boron is fixed in a lattice. It's not going to conduct. So boron over here gets a negative charge, but it does not contribute to the conduction of current. Again, the concentration is small as compared to silicon atoms. So overall the lattice is still electrically neutral, but the conduction which happens in the conduction band due to the charge carriers is due to the positive holes. Okay, so we have positive holes now contributing to the conduction of current, and the charge magnitude is the same as that of electron, right? So this is in fact a p-type semiconductor, in which the majority charge carriers are holes which are contributing to the conduction of current. So this leaves one bond position open. You see one when boron is there, having having three covalent bonds with the nearest silicon atoms. So at room temperature, what happens is that an adjacent silicon valence electrons have sufficient thermal energy. It moves into the position, thereby creating a hole. So we have a hole over here. So this effect is shown in figure 1.7b in this figure. So the boron atom has a net negative charge but cannot move, so the hole is created and can contribute to the hole current. So this is an acceptor impurity. Just like in group 5 we have donor impurities. This is acceptor because it is accepting electrons, right? It is accepting electron and it's getting negative charge. So an acceptor atoms lead to the creation of holes without electrons being generated. You see, electron is not being generated. It tends to create a majority carriers that are consisting of holes now. So this process is also called as doping, can be used to control the concentration of holes in a semiconductor. A semiconductor that contains acceptor impurity atoms from group 3 elements is called a p-type semiconductor for positively charged holes, and has a predominance of holes compared to electrons. Okay, therefore this is a p-type semiconductor. Now the materials containing impurity atoms are called extrinsic. These are extrinsic semiconductors. So in extrinsic you can either have a p-type or n-type. So it depends on by which impurity atom you are going to introduce, you are going to do the doping process. If it is from group 3 elements, then you have a p-type semiconductor in which the majority are holes. If you are going to dope your semiconductor lattice with group 5 elements, then the majority are electrons, in which case you have an n-type semiconductor. So an extrinsic semiconductor has two types, n-type and p-type, depending on by which impurity atom the lattice has been doped or impurity has been added. Okay, so doping process allows you to control the concentration of free electrons and holes, and then in turn it determines the conductivity and current in the material. Okay. Now, a fundamental relation between the electron and hole concentrations in a semiconductor and thermal equilibrium is given. This Ni is it's the concentration of charges, and concentration of charges is primarily in semiconductors due to the negatively charged and positively charged holes, negatively charged electrons, positively charged holes, and thermal equilibrium. So N0 is the thermal equilibrium concentration of free electrons over here. P0 is the thermal equilibrium concentration of holes. Ni is the intrinsic carrier concentration. Okay. So for example, at room temperature, each donor atom donates a free electron to the semiconductor. If the donor concentration Nd is much larger than the intrinsic concentration, then we can say that okay, because it's a donor impurity, and each donor atom, like phosphorus, is contributing to an electron in the lattice, and that N0 is coming from, you see this is coming from the impurity atom. So N0 is approximately the same as Nd. Okay. So if you want to calculate the number of holes, and then from the above equation, holes can be calculated from the intrinsic concentration of charge carriers, Ni square by Nd. Similarly, you can do the same for an acceptor atom, for semiconductor, which is doped by the acceptor atom, that is p-type extrinsic semiconductor. So valence electron, which is accepting a valence electron and creating a hole. So you can calculate the concentration of, you can say that okay, the major contribution of hole is due to this, it depends on the number of atoms by which it has been doped. So the acceptor concentration Na is much larger than the intrinsic concentration. We see that the number of holes concentration is equal to the acceptor impurity concentration. In the lectin concentration, accordingly, the thermal equilibrium becomes Ni square by Na. Okay, so, I mean this the concept is well illustrated in this example 1.2. What it says is that if you want to, go ahead and calculate the thermal equilibrium of electron and hole concentration, in part A, in both parts we have silicon at room temperature, 300 kelvins. But in the first part, you're going to dope this with a group 5 impurity, phosphorus. And if you recall from example 1.1 that we discussed last time, the intrinsic impurity is about, the intrinsic concentration of charge carriers was 1.5 10 cubic centimeter. This was the carrier concentration of holes and electrons. Okay, so Now, if in part A, if you are going to dope this with phosphorus, a donor impurity, at a concentration of 10 to the power 16 per cubic centimeter, then we can say that okay, majority of electrons are coming from this N-type material is going to have majority electrons, and the source is the valence electron of phosphorus. So N naught is the same as Nd, and in that case, you can see that the number of holes from the intrinsic concentration of charge carriers is much smaller. I mean, this quantity is much smaller than the number of electrons which are now there present in the lattice structure of an N-type semiconductor. So what it means is that in N-type, this is an N-doped or N-type semiconductor material, okay, which is formed by adding impurities of phosphorus into the silicon lattice, and what it shows is that N naught is much greater than P naught, and what it means is that the majority of concentration of the charges that are going to conduct current is electrons. We have electrons. Similarly, in part B, if you are going to dope this at the same temperature with boron for the same material silicon at a concentration of 5 into 10 to the power 16 cubic centimeter atoms, acceptor impurity atoms, then again from intrinsic impurity and intrinsic charge concentration, you can find out the number of electrons, and again you can see number of electrons are much smaller as compared to the holes that are being created by the boron atom. So N naught is much less than P naught over here, and the number of holes is why they are created, because boron atom is going to accept adjacent electrons, and that in turn is going to create hole over there, right? And these number of holes are larger in a p-type semiconductor. This is a p-type semiconductor, so number of holes are larger as compared to number of electrons, and this in turn you see turns out that in a p-type semiconductor the majority of concentration is holes, which is going to contribute to the conduction of current as compared to electrons in the N-type material. So we see that the semiconductor doped with donors, the concentration of electron is far greater than the holes. Conversely, in a semiconductor doped with acceptor, the concentration of holes is far greater than that of electrons. Now, it is also important to note that the difference in the concentration between electrons and holes in a particular semiconductor is many orders of magnitude. But the idea is straightforward. You see, if you have a donor impurity like in part A, like phosphorus, arsenic, or antimony, you have the valence, you have extra valence electrons that can get enough energy at ordinary room temperatures to break free from the bonds, and they can get elevated themselves to the conduction band and they can start conducting, right? So electrons are coming from the valence electrons of the donor impurities, and in such semiconductors which has been doped by group 5 elements, the majority carriers are electrons. The majority carriers, free roaming electrons at room temperatures, are electrons. Conversely, in the p-type semiconductor materials, you have an acceptor impurity, which is going to create holes instead of electrons, okay, to complete its octet structure. But then, owing to the creation of more holes, you have positively charged carriers, which are predominant as opposed to electrons in the lattice now. Okay. Now, in an N-type semiconductor, just remember the electrons are called the majority carriers because they far outnumber the holes, which are termed as the minority carriers. In contrast, p-type semiconductors, the holes are the majority carriers and the electrons are the minority carriers. Okay, so that's about the extrinsic semiconductor. Why we dope a semiconductor is just to control the concentration of charge carriers. They can be p-type, they can be n-type. Okay, both constitute in the mechanism of current conduction, and by doping you can increase the concentration of charge carriers and increase the conductivity of the material as opposed to in the intrinsic or pure semiconductors. Okay, that's all.